title of my presentation is Neuroinformation Processing Machines. And I'm going to present in the beginning neural computing engines. You will see it's about information representation in the time domain, the spike domain. And then I'm going to elaborate a little bit on spike processing. Also, I'm going to discuss phase processing. And finally, I'll talk a little bit about a fruit fly project, which I'm driving. So the original work here started some, 15 years ago. I started a little bit later, but this work was done here at Berkeley. And I'm just going to show quickly a video.
Dan have proved that in principle it is possible.
Let me just stop here the audio. So what I'm going to do is just feed forward here. So what you see here is basically recordings. This is Yang Dan here from the biology department here at Berkeley. And so what they did is they did some recordings in the LGN in the cat. And here is what you see. On the left is the input. And they took the output from the LGN and they decoded it with the simple decoder. And you can see, roughly speaking, what sort of quality they got. On the left is the original, on the right is what they decoded. So that means essentially that, at least in the cat, in the LGN, information seems to be represented fairly precisely. Most likely, the problem here is the decoder itself. And so this was sort of a starting point for my work in this. And I started looking basically at understanding whether this issue, which is sort of maybe not so interesting from a neurobiology standpoint that information is represented, but it's very interesting from a quantitative standpoint. And the fundamental questions which we started asking are of the form of the type, why are there, let's say, 1 million axons in the vertebrate retina, and why are only 20 to 30,000 axons in the cochlea? So that sort of suggests that when it comes to information representation, the number of neurons plays a big role. And we wanted to find out quantitatively whether actually we can go and come up with some good answers for this. There are questions of the type, would 500,000 neurons or neuron axons suffice to represent information in the visual field? So the fundamental problem, therefore, from our standpoint is come up with a model. And here I have a very simple model where on the left you have the visual field, so it's, let's say, a movie. And this is presented to a neural circuit which consists of receptive fields. These are linear operators, followed by spike generators, essentially axon hillocks. And the number now is variable, okay? As you will see later on, the number can actually grow very large depending on what sort of signal one presents to this. And so the question which we raised was a classical information theory question, which is, suppose that I know the encoder, meaning I know the linear operators, the receptive fields, and I know the nonlinear operators, the axon hillocks, and I observe only the spike trains like a receiver. What can I say about actual information being encoded? So the class of models we looked at, they are very general. And here, first, on the left, I show a general filter. So it's a space-time filter. It can be also three-dimensional, but here I'm showing it two-dimensional, so X, Y, and T. And then we have a biological spike generator, which is described on the right. Let's say the typical system of differential equations come from a Hutchinson neuron. So there are 4 differential equations, pretty nasty. And I'm just showing the deterministic case, but of course, it's of interest also to look at the stochastic case. So now, this is a very general statement, except possibly for the dendritic tree as being modeled with receptive fields, which are linear, but as you will see later, I'm going to show that we generalize this for nonlinear operators, both in the dendritic tree and also as far as the biological spike generators are concerned. Now, since Jacob mentioned that this is all about foundations, I would like to emphasize what we found out from a theoretical standpoint. Here I'm showing a model which is being used in neuromorphic engineering oftentimes, where the biological spike generators essentially encode either positive or negative signal only. You can see here on the left, full-blown cycling, in the three-dimensional space. We cannot show it in the four-dimensional space. So there are limit cycles. And so this is when the problem gets extremely interesting. It's very complicated. Here on the left, you can see that the signal is negative and positive. So one of the neurons encodes only the negative part of the waveform, the other one only the positive parts. You can see the spikes there, and how essentially the two neurons alternate in encoding. But what we found out fundamentally is that what the neuron is doing is essentially doing a linear operation on the signal U, which is x, y, t, and that operation on the right-hand side consists of two terms. One is Q and the other one is epsilon. Epsilon, essentially, look at it as being noise. And Q is a quantity which a receiver can compute from the spike train. And as a result, we have rewritten this through simple math, that this operation here can be written on the left-hand side to be an inner product between the signal and a class of functions. And the right-hand side as before. Now, what's interesting about this, since it's an inner product, what it means is now that what the neuron is doing, the axon hillock specifically, it takes a signal, let's say in 3 dimensions. I have a signal here like a force, a vector, and what it does is it projects it on a set of coordinates, okay? So here's 3 coordinates, and in physics, of course, we pick the coordinates to be orthogonal, but here the coordinates are not orthogonal. They are generated by the neuron in real time. And what is really interesting is that these functions here are function of the signal itself. So the projections, the axis in this space, they're actually generated by the neuron, by the axon hillock in real time. So while that means that the inner product is more complex than what we're used to, the geometric representation of this is beautiful because suddenly you understand what the neuron is doing. What it's doing is computing inner products. And so what it means now is for a neuromorphic engineer that if you have a crappy implementation of your neurons, it doesn't matter. You just have to know what it is. Because essentially what it does is computing inner products, and once you have this projections on inner products, like in linear algebra, of course you can recover the signal by doing an inversion. And so what the neuron therefore is doing, the axon hillock, not the soma, the axon hillock is doing a sampling as we are used to in information theory and signal processing. And so therefore, from there, we can recover the signal with arbitrary precision. And in particular, we can set this up, the usual way with cost functions, as is shown there. I'm not going to go into details of this. Suffice it is to say that the representation U is like in support vector machines where you have to pick a kernel, and the kernel here is phi, and it just happens to be a sinc function because we are working with band-limited functions. The formula is very similar, and as a result, it's actually very powerful because the type of theorems we can prove are of the type that of the Shannon type, if the average number of spikes at the output here of this encoder, if the average number of spikes is beyond a Nyquist rate, perfect recovery is possible. So it's like you have an A to D converter without a clock. Okay, it's an A to D converter based on spikes. You're looking at the average number of spikes. But with the decoder there on the right, you can recover the signal with whatever precision you want to. And this is now on very solid mathematical footing. And it's very clear what the implications are when you can do something and you cannot do something. Therefore, in vision, you have 1 million axons. Why? Because the bandwidth of the signal is 6 to 8 megahertz. In audio, you have 20 to 30,000 axons. Why? Because the bandwidth of the signal is 20 kilohertz, if you can go as high as that, okay? So now demonstrations. Here is a demonstration where we have a bee in a natural environment. On the top is the original signal. It's an HDTV signal. It has 360 by 640 pixels. And what we did is, on the right, we have recovered the signal. As you can see, there's no difference between the two. There's no difference between this signal here and the recovered signal here, okay? Now, here we added noise to it, and we did 10 times more noise on the right, and if you look carefully, you can see that there's pixelated. So we're arguing this can be demonstrated in neural hardware. We are doing this on GPUs, but if you do it on GPUs, you can do it, I presume, also in hardware. Now, what's interesting is to look at dimensionality. There are roughly 100,000 Hodgkin-Huxley neurons. So remember, one Hodgkin-Huxley neuron, nobody understands. There are 100,000, okay, there. And the problem is solvable, okay? And in a sense, it shows that there is a way to get to the bottom of this by understanding the underlying structure of the problem, okay? The circuit can have, it can be just parallel, it can be, interconnects, feedback, what have you. Now, sorry. So now, of course, from a theory standpoint, what we like to do is you would like to understand, the relationships. And here is a question, typically, which comes up in neuroscience. Average number of spikes, people cannot relate to it well. But they can relate, at least in neuroscience, they can relate very well to the notion of number of neurons. So what we did here is we're demonstrating what happens if we increase the number of neurons. The screen size is here much smaller than what we had before. It's 90 by 160 pixels. The original is here. And what we did here is we used encoders with, let's say, 30,000 neurons, 40,000 neurons, et cetera, et cetera. And now you can see here what the difference is. So obviously here, the quality is much lower, and it's given in SNR. I think it's very important to start actually specifying this data in SNR, because this is what we are used to in IT. And as the number of neurons goes up, obviously one comes closer and closer to the actual original, as demonstrated here. So we have a complete understanding now of the trade-offs in terms of number of neurons. If now we play a different game whereby we are playing out the video faster and faster, the quality goes down. Why? Because the bandwidth goes up. So if this is a sampler, your circuit is a parallel sampler. Obviously, if the bandwidth goes up and the sampling rate is the same, meaning you generate the same number of spikes, then in the end, what you end up is that the quality of the playback goes down. Now, the problem setting here is coming out of information theory. It's coming out of signal processing. It's coming out of communication theory. This is not how people in neuroscience think about this. You go into a lab, you do experiments, you have a neural circuit, you apply a signal to it, and then you observe the output, and you try to infer what it's doing. So, in other words, what we did, we made the assumption that the circuit is known, the encoder is known, we observe the output, and then we ask what is the input. But as I said, in practice, in the lab, in the neurobiology lab, these filters here, the receptive fields are not known. And so what do? You apply a signal here at the input, and you ask the question, knowing the input and knowing the output, what can you say about actually the receptive fields, how they're encoding information? And here we have a very nice result, which says essentially, which is based on a very simple observation, which is if these are linear operators and this is the input, then there's a convolution between the two. And convolutions are commutative. And so what that means is that you can put the signal as being the impulse response of the filter, whereas now the input, what it is actually the impulse response of the filters themselves. Okay, so we essentially swap the two. And when you swap the two, then you end up with a classical neural encoding problem, which we just solved. Okay? So you see here, these are all used. They are controlled in the experiments. Okay? The H's, the filters are not. Now there is also P in front of those filters, and that means a projection. What does that mean? Well, from a practical standpoint, if these filters have a larger bandwidth than the input signal, okay, then of course you cannot explore, you cannot find out, what is the actual value of the filters because you're not driving them, okay? So what you have to do is you have to drive a wide bandwidth. And people in practice, oftentimes they use white noise. White noise leads to problems. Here we have band-limited signals. So these projections are nothing but, in the Fourier domain, it's like you apply a sort of a brick filter to the Fourier transform of the filter themselves, and then you focus only on that part of the filter, and this appears as an input here. And this is important now from an experimental standpoint because people oftentimes, they are not aware of this. They repeat the experiments in different labs and they get different answers. And you see, the results here says be careful about what sort of bandwidth you're operating with because that has an implication of what are you going to identify. And I'm showing here an example now in which what we do is we start with the circuits as being unknown. We identify the circuits. We then assume at the decoder that the identified circuits or filters are the real ones. We take then a new signal, we encode the new signal with these filters, and we decode it. In other words, we do here a comparison now in the input space, not in the output space as typically is done in machine learning. So let me just repeat this again. I have a circuit which I have to identify, okay? And in the end, I do identify it. Once I have this, then I apply a new class of signals, okay? And I can invert the circuit, and I can compare the original signal with the decoded signal to see, how well it is working. And this is intuitively way more powerful than comparing spike trains in the output space. Because, if you see the distance between spike trains, what does that mean? Intuitively. We have no intuition about this. Whereas, as soon as you see the videos, you know exactly, what is the quality of your filters in identification. Okay, so here at the left, the quality is pretty poor. And as you go to the right, where you repeat the experiments, the quality gets as good as you will like it to be. So, great. Now, remember Bruno yesterday mentioned that it's very important to focus on neurosignal processing in the DDD tree. And here's an example. We worked this out for the case where we have actually general Volterra operators. So the filters can be nonlinear to the extent you would like them to be. And here we are showing an example with complex cells. And what you see here on the left, basically there are filters followed by squaring, sort of energy operators. And then we pass them through spiking. And here is the identification of these. You can see this is now a space-time identification. The space is x, the time is t, and we're showing, depending on the number of trials, how good the identification is. So again, this is a very good understanding of what's happening also in the case where you have nonlinear processing. So there's no issue about nonlinear processing as far as we can see now. The issue is to find now good implementations of this, find out good encoders, what have you. Spike processing machines. Okay, so fundamentally, until now, I focused on information representation using time encoding machines. So here's the visual space, and I like to understand how many spikes I need to represent it. And I argued that Nyquist rate is fundamental to this. Now what we like to do is we'd like to take these spikes here, pass them through a processor, spike processor, and do something interesting. And so this is tricky. So what we did is, the first example I have here is the encoder, here's the decoder. And what we did is we started shuffling the connection between the encoder and the decoder according to certain permutations, which we worked out theoretically. And what we found is that basically this way we can implement rotation, translations, and scaling. These are operations which are very interesting in vision because we do recognize an object no matter how it is translated in space, how it is rotated, or the scale of this. And you can see it here. In the first example, this is the bee. This is the identification or the decoding of the bee in this circle of interest. Here is the bee is rotated by 45 degrees. And here is rotated by 171 degrees, and this is done in spike domain. Okay? Here we are showing a similar example where what we do is we are doing zooming out and zooming in. So this is zooming in. Again, it's the spike domain. It is zooming out in the spike domain and zooming out and translation. And there's a demonstration that actually, by manipulating spikes, this is what you end up with. You can see it. The power of this is that now suddenly we have intuition about this. And so I have become a huge fan of this. I'm showing here a different type of processing whereby I take 3 colors, a single eye. Okay, so this is a single visual field. I have 3 colors. I pass them through 3 receptive fields, color, RGB. And then I play it out. And so here is, I play it out with the 3 colors. This is the original, this is the recovered, this is the error, the difference between the 2. But what we can do now is, in addition to this, in spite of the fact that the spikes represent in a complex way the 3 colors, we can decode the colors separately. So you look at the same spikes, and they are not labeled. You don't know what R is, you don't know what G is, you don't know what B is in terms of spikes, but it's possible to decode it. And this can be done also with 2 eyes. I'm demonstrating here black and white. Of course, this is a 3D video now. You would need glasses. I don't have so many glasses. But just believe me, this is the original. This is the recovered one. And now you see we can decode separately what the left eye and what the right eye are seeing by processing the spikes. And finally, we can do the same thing in color, as you would expect. So I have 2 eyes, 3 colors, all is sort of multiplexed together. They all go through the same circuit of neurons. There are something like 66,000 neurons here for the screen size. And we can recover the signal from each eye separately and each color separately. So, in other words, this is a demixing operation. Now, what I found sort of more interesting is mixing where we take audio and video. So here is the circuit. You see there are neurons here in common. We apply audio and video to the signal. And this is receptive field for audio, it's a function of time. This is receptive field for video, it's X, Y, and T. So actually the dimensionality of these receptive fields is completely different. We add up the signal, so it looks like a mumbo jumbo, basically, okay? And interesting enough, we can decode it.
Very small amount of mass may be converted into a very large amount of energy.
We picked up an old video from essentially the late 30s with Einstein, and what we're showing here is the original video, the decoded video. This is in the spectral domain, the video. Here is the audio, the recovered audio, and the results in the spectral domain. And just by looking at it, you get this feeling, oh, this is possible. So let me play it again.
Very small amount of mass may be converted into a very large amount of energy.
Could you recognize what he's saying? There must be some physicists here. Very small amount of mass, et cetera, right? Surya, this is, right? So it's possible to demix the signals. This is what we are demonstrating as a spike processing operation. Now, the main theme here is spike processing, where we started believing that it's very important to also look at phase processing. And here we are inspired by work in the fruit fly. The early vision system, retina, lamina, medulla, has roughly 60% of the neurons in the flying brain. And they are all graded potential neurons, no spiking. Okay? And we know that the fly has a good sense of detecting motion. And here we implemented 2 encoders, classical encoders. One is the right-hand motion detector. The other one is the parallelic motion detector. And you can see now what happens if we change the contrast. When you change the contrast, this motion detector is actually there under stress. They're not doing so well. And we started looking at a new class of detectors, which we call phase-based motion detectors, which I'm just going to sort of briefly give you an idea about here. But you see, there's a different class of problems here. We started talking about basically introducing motion detection on the visual field. And so we started looking at a phase defined in the classical way through the Fourier transform. But as the global phase, the implementation, what we have done is using local phase. This requires some analysis. I'm just sort of flashing this to you get a sense of what type of work this entails. And then we started looking specifically at phase locally in the images. And here is the implementation of this. The phase detector actually works better than all these detectors I just mentioned before. And the reason why we got into this is because we know that when it comes to representing edges, phase processing does a much better job than anything else. But it's much harder to do. Why? Because phase is a nonlinear operation. But as we have discussed this in the past, nonlinear processing is really the interesting thing. So that's what the focus is here. So finally, I'd like just to mention a project called the Digital Fruit Fly Brain. And the reason why I'm mentioning is because I strongly believe that it's time to have the fly brain in silicon. And we are looking for maybe next generation projects. I think that this is very interesting. And I just like to very briefly mention what we're doing. Essentially, this is a system architecture where we started implementing. What you see here is on the left, the fly as a biological organism. It's a model organism. Genetically is the organism of choice. And on the right is the robotic fly. And what we started doing essentially is build two entities, open source. One is called NeuroArc. It's a database. And the other one is NeuroKernel, which is like an operating system, which does emulation on any circuit you would like to. Now, what's interesting from a neuroscience standpoint here, this is a topic more for neuroscientists than IT people, is that what we are doing is essentially we are loading the database with biological data which is out there, but the whole system is open source, and what we started doing is publishing requests for comments as I'm used to from the internet or designing the Linux operating system. So there are papers published with code backing them up, and this is a different way of publishing in neurosciences. It's not different than IT. In IT, we are used to this. It's a way to essentially give out some control in software development, but also gaining participation in letting people actually to build something interesting. The reason why we are doing this in part is because it's extremely difficult in neuroscience to come to some agreement on anything. So then we feel that what has to be done is come up with a design which is open, but not open in the sense that a group of people control 20 million lines of code, but basically that the architecture consists of building blocks, and these building blocks can talk to each other. So specifically what we have done is we modeled basically the fruit fly as being a set of neural pills but they intercommunicate. So if you're an IT person, what that means is we look at the brain as if it would be a computer board on which you have chips. And the chips can be designed by anybody and any way they want to, but they have to talk to each other, which means they have to talk to the bus, and there has to be a standard API to exchange information. So that's exactly what we have done. We published an API so that people can design neural pills called here local processing units. And the architecture is, as shown here, consists of three planes. This is the plane of the programmer. Then you have compilers, resource allocation on the level of the CPUs, and then the GPUs have direct communications. And so it's a view of designing a programmable network, if you like. And so we have experimented with this. Specifically, we have published an API, and if you look at here, this architecture, let's say for the early vision consists of retina, lamina, medulla. They can be developed by independent groups, but if you have the APIs, essentially this can be plugged together, you can compile it, and then you can run it. And here is my last slide. Here's a emulation of the fruit fly brain retina. And I'm back now to the starting point where I showed the LGN in the cat. I have it now here in the retina of the fly. And this is a model based on neurophysiology. It's vetted against data. And now, suddenly, it's not that we are looking at a single neuron and what's going on in terms of waveforms. We see the entire picture. And the picture is, here is the visual field of the fly. The fly is moving around, has been moving around. Okay. You see the fly is moving around, has a certain visual field, and now we can see exactly in what way the retina is actually representing information. Now, if you start changing parameters in the photoreceptors, a part of the retina, you essentially immediately see it visually, the effects. And I think that this is by far more powerful, and it's inspired actually by standard circuit design, where you come in with an oscilloscope and you want to find out what's going on. But now you see the oscilloscope is across the entire retina. It's not just some specific neuron and all this, and you look at the waveform, and it's very difficult to get an intuition. As soon as you do this, you suddenly have the feeling that, quote unquote, intuitively you understand what you're dealing with. So I'll stop here.